lecture, and first lecture it will be a story of I titled it The Quest for Fundamental. So fundamental, it means um, we'll start with the philosophy why people wanted to know about the fundamentals. Okay, so it has been in our civilization, I mean, with different civilization also. So they always wanted to know the fundamental building blocks of matter. Okay, so suppose if we have anything in front of us, say this glass, so you can cut in pieces and finally you will find out these are made up of atoms, or maybe table. So if you cut it off, there will be cells, and then further it will be made up of some hydrocarbon like carbon and hydrogens, so a lot of several elements. So thing is that fundamental is key. So what does it mean by fundamental? It means it does not have any internal structure. Okay, so I think we already heard several times in several civilizations, there were fundamental elements like earth, water, fire, etc., whether it is Indian civilization or Western. So the story of nuclear and particle physics, how it involved, is the quest of fundamental, knowing about what matter is made up of and how do they interact. Okay, so little bit fast forward to Dalton's atomic theory. So we figured out there are elements, and those elements are made up of several atoms, different elements made up of different types of atoms. And those atoms at the time of Dalton, around 1800, they were considered indivisible, means it cannot be destroyed. Okay, so they arranged in a fashion, it's called a periodic table. But the question that we pose is atom, the story end there? Like, is the atom fundamental? Is it made up of something? So by now you all know that atom is not fundamental. And what is the first elementary particle you can think of coming out of atom? Okay, electron. So since we are going through the discovery, the story timeline, so the first thing that said that atom could be divisible, or some elementary particle popped out from atom, was electron, and it was discovered by J.J. Thomson. And this is his famous cathode ray tube, in which electrons were produced by thermionic emission. So there was some metal plate, tungsten maybe, and it was heated, and then electron popped out, and then you put some potential difference, it accelerated, and then you do several experiments to measure some quantity, like Thomson measured the E by M ratio, and so he put electric field and magnetic field, and measuring the deflection, he figured out the E by M ratio. Okay, so this was the actual setup of Thomson. The pointer, yeah. Yeah, so this is the schematic. Okay, so as I was saying, electron was emitted through the thermionic emission, and this is the plate where you heat it up, and you put it in the electric field. It is accelerated towards this, and then you put electric field and magnetic field perpendicular to each other, and you try to cancel out the different field, and you measure the deflection in the glass. The end screen is graduated, and you measure the amount of deflection, and you measure how much electric field you are applying, how much magnetic field you are applying, and then you calculate the E by M ratio. So this is a question I pose, and you should write it down and think about it during lunch time. Okay, and we will discuss it, how E by M ratio can be calculated from the Thomson's apparatus. Okay. Okay, so hint is, I think those MSc in medical physics, I think students already have done this exercise, but still. Okay, so Thomson measured this E by M ratio by, the hint is by cancelling the deflection by applying appropriate amount of electric field and magnetic field. So that's a hint. So anyway, let's come back to the result. So what it was found, what do you expect if I try to calculate the E by M ratio of a proton and an electron, which one would be higher? Electron, right? Mass is, the charge is similar, although it's negative and positive, but the mass is very, very tiny, 1,700 times tiny. Okay, the E by M ratio is found to be, large. E by M ratio is found to be very large for the electron because mass is tiny. So later it came to know, later Millikan measured the charge of the electron and figured out, okay, there is something, some different particle. So it's which came out of the atom. Okay. So now we know from the work of Thomson and Millikan the charge and masses of, because you know the E by M ratio, you know the charge. So charge and masses are known separately for this electron. So let's try to build up a model. So you have a neutral atom, okay, and you know that there are some negatively charged particle which are electron which is coming out. So you try to put together a simple model where you think of your entire positive charge is distributed in a sphere. I would call it maybe a watermelon kind of model. So you can, red flesh is the positive charge uniformly distributed, and whereas the seeds are the electrons. Okay, so when you heat it up, it comes out. Okay, so one good thing to remember is electron volt, definition of electron volt. So it is the 1 electron volt is the kinetic energy gained by electron when you put a potential difference of 1 volt. Okay, so can someone tell what is the value of 1 electron volt in joule? Okay, this value you already know. Okay, so you can keep this, you can write all those numbers. So now we have electrons we discovered. Okay, so moving fast forward to 1906, people were doing experiments with alpha particle. They were hitting alpha particle in several foils, mostly students of Rutherford. Okay, so this is the setup of Rutherford experiment. So this tube you can see here is mostly, you connect it to a vacuum tube. This is a schematic. So you connect this cavity to a vacuum tube. So you pull out all the air. Why you need to pull out air? You're doing an experiment with alpha particle. Why you need to pull out air? Yeah, okay. So, you know, the alpha particle range in air is about centimeters, right? So if you want it to hit the target here, which is the gold foil, you need to pull out the air. So, so this setup is in the vacuum, and this is the source of alpha particle. I think it was radium or americium 241. I do not remember exactly, but it has to be a monoenergetic. Okay, why alpha particle coming from nuclear decay is monoenergetic? Because it's a two-body decay. Okay, so it's a monoenergetic alpha particle, and you make a collimated. You try to make a collimated beam, and it hit a gold foil here, and how do you see it? How do you observe the alpha particles? Okay, so you put a microscope and you coat the surface of the microscope with a zinc sulfide screen. So whenever your alpha particle hits the zinc sulfide screen, it produces a scintillation photon. Okay, and you just see through the eye. Okay, and this entire setup is rotatable. Okay, so this microscope can rotate at different angles, and you can measure the angle of scattering at, so you perform the measurement, you count at one particular scattering angle, you keep on moving, and you count the alpha particles scattered. Fine, this part is clear, right? Okay. So coming back to the schematic, I think you guys already know that alpha particles are helium ion, so 4He2, and so this is a schematic of the same thing. So I do not have to describe again, but I just wanted to bring your attention towards observation. So a majority of alpha particles are scattered at small angle. What do you mean by small angle? It means they were just undeflected. Okay, majority were undeflected or deflected very slightly. Okay, and a small fraction, majority, okay, a small fraction is found to be scattered at very large angle, okay, about greater than 90 degree. So that amount is about a small fraction, and almost 1 in 15,000 alpha particle, it was backscattered. Okay, so that was more surprising for Rutherford. Actually, this experiment was done by his students. Okay, and Rutherford interpreted the result. Okay, so this was very surprising that something you hit and it bounced back to you. Okay, so why it is so surprising, we will see in a moment in a simulation. So let me just pull out this one. So if we think of a plum pudding model, and so you can see here the red part is mostly positively charged from the Thomson's model, and if you try to shoot the alpha particle, it is mostly passing, right? Not much. If I track, it's mostly undeflected. Okay, and if I try to pull out the Rutherfords, okay, and you shoot the alpha particle, and if you just observe this screen, okay, so a majority of them are undeflected. A small fraction would be deflected by a large angle, and if you wait for enough time, you will see a backscattered alpha particle. And actually, you can go to a, this is the atomic scale, and you can go to a nuclear scale, and you can put the traces. Just observe the trajectory. We'll come to it in a moment. So you can see how they are getting deflected coming to. So this is a very zoomed up picture of it. Okay. Okay, so just observe the trajectory for a while. Okay. So anyway, so coming back to our lecture. So what I wanted to convey, that large scattering cannot be explained based on Thomson's model of atom. Why is it so? Because you know, the force between alpha particle and the nuclei is Coulombic, right? And you know that it depends on the charge of the nuclei and the distance between them. Okay, so if you, for the backscattered, you want to, what you want to do, you want to maximize the thing, right? You want to have the entire charge as well as distance to be smaller to have the maximum impact. So if you imagine a Thomson's model, which is uniformly, nucleus is the atom is entirely uniformly charged sphere. So you cannot reduce it. If you try to reduce the distance, the charge will be you will be feeling lesser and lesser charge, because it will pass through your atom and you will feel only the charge which is enclosed inside this radius, right? But if you try to go further, you feel the entire charge, but the distance becoming larger. You're getting my point? Okay, so this backscattered thing, the maximum deflection, it cannot be explained based on the Thomson's model. So to have the backscattered thing explained, you need to imagine the entire charge of the nucleus is concentrated at one center. Okay. So as I mentioned it already, so you need to have the entire positive charge of the atom. It has to be contained in a very small sphere, and we call that small sphere as nucleus. And whenever the alpha particle passes closest by to the nucleus, it experiences a strong electromagnetic force. Okay, because it is now passing very small distance and it is experiencing the entire charge of the nuclei. Okay, so since the force experienced by alpha particle is central, the trajectories are hyperbolic, right? You have already seen the trajectories of alpha particle in that simulation. So those trajectories are hyperbolic, okay? And this also you know from your classical mechanics. If the force is central, the trajectories will be hyperbolic. Okay, so this is the schematic. We'll discuss Rutherford scattering and we'll calculate the scattering formula into tutorial session. But few things you should remember. So this is your scatterer, your nuclei, which is Z times the charge on the electron or on one proton. So and this is the distance away from which the alpha particle is passing. So this you call impact parameter. Okay, and if you connect this line, the asymptote of the track, okay, and the two the angle which is formed between the asymptote of the two tracks, like incoming and outgoing, that angle is called theta, the scattering angle. Okay, so this part you should just understand what is scattering angle as well as what is impact parameter. Okay, so what happens to the scattering angle when you try to play with the impact parameter? So this is your impact parameter when, so now you know that if you try to reduce the impact parameter, then scattering angle will be smaller or larger? Larger. You can see that in the diagram, right? Because you're going closer and closer to the nucleus. Impact parameter is reducing. It means you are going closer and closer to the nuclei, right? You can see it here. So I've drawn here the 4 scenarios, 1, 2, 3, 4. The scenario number 1, in which the impact parameter is very small, okay, and this, it is the most scattered one, right? Scattering angle is very large. Okay, so this is the thing you saw that in the simulation. So most of the tracks are hyperbolic, and these are plotted as a function of impact parameter and different scattering angles. Okay, so in the tutorial, we'll try to deduce this relation, that impact parameter is having this constant, which is z prime. Z is the charge on alpha particle, Z prime is the charge on the nucleus, divided by some constant, divided by the kinetic energy of the alpha particle, mv square sum factor, and cot of the scattering angle divided by 2, right? So we'll try to derive that in the tutorial. Okay. So let me just fast forward to the result, and I will just try to explain the result, interpret the result. But will just to mention that that was the relation between the impact parameter with the scattering angle, and then we'll also derive. This is called the Rutherford scattering formula, and we'll derive this, and we'll see it later. But let's come to the result part of it, okay? In the lecture. So these are the, so now you imagine this setup that I mentioned earlier, this setup, right? So what you are doing, so you are putting a source here, you are putting a gold foil, and you are moving your microscope at different angles, right? And you are counting it for some time. So that is the thing. You fix it at one scattering angle, theta 1, you count it for 10 minutes, you move to theta 2, count it for 10 minutes, so on. So these are in the first column that you see is the scattering angle. Okay, so 150 degree, 135 degree, and so on. And you want to take out any other parameters which is not coming from the scattering, say for example background or scattered through the cavity of the lead box where you're keeping the source. So you measure it without foil first. Okay, you don't put a foil, and then you put a foil, and then you subtract it off. So without foil, you might observe some count. Okay, with foil you observe some count, and you subtract it off. So this subtraction will give you the actual count of it, right? And suppose you are counting for 10-minute window, you take account of the decay also. Okay, because in 10 minutes I think the activity is falling down, so you take account of that factor as well, and then you ultimately come out to be the corrected counts, say 10 minutes. Is it clear or any confusion here? Right? So this last column is corrected by taking out of any background thing, corrected by the radioactivity also, radioactive decay also, right? And then you calculate this factor 1 upon sine to the power 4 scattering angle, and if you multiply, it leads to a constant, right? So if you try to multiply or if you just try to plot the scattering angle and this number of counts, you see a nice dependence on the cosec to the power 4 theta by 2, right? So this one is first observation you can see, but if you try to multiply by 1 upon this, you will see a constant. Is this part clear? So this was the validation of the Rutherford scattering formula that you see here. Okay, so other thing from the Rutherford scattering formula is we can conclude is that number of scattered alpha particle was found to be proportional to 1 upon cosec to the power 4, or sorry, cosec to the power 4 theta by 2, or 1 upon sine to the power 4 theta by 2, right? So this was measured, this was found experimentally, as well as we will see, try to calculate it. The other thing you might notice, can you tell me, looking at this formula, how the scattering is related to the kinetic energy of the alpha particle? Just look at this formula and tell me. Huh? So how the number of scattered alpha particle is related to the kinetic energy of alpha particle? I cannot hear anyone. Just look at, huh?
Inversely proportional to the square of kinetic energy.
Okay, very nice. Inversely proportional to the square of kinetic energy. Anyone, all of you can see, right? There is a mv square term, half mv square. Half mv square is the kinetic energy, and there is a square term, right? So 1 upon kinetic energy square of the alpha particle. And I don't have to go back. This part is also clear that the number of alpha particle is proportional, scattered alpha particle is proportional to the z square, which is the foil's atomic number. Okay, other thing which does not come from the Rutherford scattering formula is the thickness. Okay, this was found to be found experimentally, and if we try to increase the thickness, number of scatterers increase, right? Number of atoms, number of nuclei increase. Okay, so number of scattered alpha particle is proportional to the thickness of the foil. Okay, that you observe here. Okay, moving on. So from the Rutherford experiment, we found that nuclei is a point charge, concentrated point where all the charge of the positive charge of the atom is accumulated, right? This was the conclusion from. But can we get an estimate of the nuclear radius from the Rutherford experiment? Can we say something about what is the size of the nuclear radius? Anyone? Femtometer, but how? From the Rutherford. Okay, so what you do is that you know the kinetic energy of the alpha particle. How do you know the kinetic energy of the alpha particle?
It is inversely proportional to.
Who is saying? Can raise your hand? Yeah.
It is inversely proportional to scatter of angle of alpha particle. So.
But without, if suppose I give you a radioisotope, And can you know the kinetic energy of the alpha particle? I told alpha particles are monoenergetic, right? Right. So how it is coming? Because it's a two-body decay. So just by knowing the parent nuclei, daughter nuclei, you can know the kinetic energy of the alpha particle, right? Just from the two-body decay physics, right? So you can know the kinetic energy of the alpha particle. It will be mostly a monoenergetic, right? So what was the question? So now you know the kinetic energy of alpha particle. You look at the backscattered one, only the backscattered alpha particles, right? So what happens? Alpha particle is coming from this direction, nuclei is here. The alpha particle will reach to some point where its kinetic energy will equal to the potential energy, right, gain, and then it will go back, right? So you try to, just from the kinetic energy of the alpha particle, you equate it, half mv square equal to the potential r min. R min is the distance closest it can go to the radius, okay? So this will not give you a actually radius of the nucleus, but it will tell you how close I can reach. And from that, you can say that, okay, my nucleus is not there till now. You can put an, if I say it more technically, I can put an upper limit on the size of the nucleus, right? I can say that at least nucleus is not here, I came back. Okay, alpha particle came back. So equating this, R mean, I rearrange this equation, equating this, I can calculate an upper limit on the size of the nucleus, right? And from this calculation, I can figure out it happens to be 27 femtometer. Okay. But it's a very, I mean, you will come to know in a moment that 27 femtometer is a large number, but quite good. We reached up to femtometer. At least I can say that the nucleus is of the order of femtometer, as you said, right? So this was it. What is another way to measure from Rutherford-like experiment to find the size of the nuclei is that you keep on increasing the kinetic energy, right? You keep on increasing the kinetic energy, and at one point the Rutherford scattering formula breaks. So what we are doing is that there is alpha particle that you are shooting to the to the gold foil, and you put a detector fixed at some angle, say it is 60 degree, okay, and you keep on see the scattered alpha particle, take a count. So what we are doing this time in the x-axis is not the scattering angle, this is the kinetic energy of the alpha particle, right? And you see how, if the Rutherford scattering formula is valid, how this curve should look like. If you try to fit, which function you will fit?
Or minus 6.
Huh?
Decay from 60%.
Why?
It is decreasing like this. The plot is like this.
What I'm plotting in the x-axis, what I'm plotting? Huh? Kinetic energy of a particle. So how does it go? Number of scattered to the kinetic energy, how does it goes like? So 1 upon x square, right? So you will fit it by 1 upon x square. So you will, this dotted line is 1 upon x square, right? So you try to, and these are the dots are the experimental curve. So this is your theoretical curve that you said 1 upon x square, and at certain point, the Rutherford scattering formula breaks. Why it breaks? Because you guys are all in MSc, so you should be knowing how many forces are there. 4, right? So Rutherford scattering formula is based only on electromagnetic force calculation. Till now, we have not considered that strong interaction is there, right? So if you try to come very close to the nuclei, strong interaction will just start, okay? And it will show some deviation in the Rutherford formula. So after this point, Rutherford scattering formula won't be valid, it breaks, right? So at this point, you will say, okay, I touched the nuclei, right? So from there, you can calculate the nuclear radius, and we will try to calculate in our tutorial, okay? And we'll figure out the answer will come roughly about 10 femtometer or lesser than that, okay? So this was, so till now, what what was our story title? Quest of fundamental. We were trying to figure out what are the fundamental things, what matter is made up of, right? So we figured out it was made up of atom. Atom was found to be not fundamental. It is made up of electron and nucleus. So is nucleus fundamental? No. Okay. So after this scattering, somebody was saying yes. Is nucleus is made up of something? Proton and neutron. Okay. So same Rutherford discovered proton. Earlier, I think proton was known. How it was known? People were doing this cathode ray experiment, right? There were also canal rays experiments where ions were. So if can I call proton as hydrogen ion? Safely I can say, right? So you can figure out in canal rays, right? But it was more saying proton as a constituent of nuclei. It came from Rutherford. Okay, so these were already known. Okay, and it is figured out that hydrogen ion had highest charge to mass ratio, and Rutherford revealed the presence of hydrogen nucleus or hydrogen ion or proton, and discovered as proton. So what he did, he bombarded alpha particle with nitrogen, okay, and figured out it gave off oxygen and proton. How Rutherford will how this setup would look like if I try to put nitrogen there? You just take out the vacuum, right? It will fill up with air, and air 70% is nitrogen, right? So if you just do that experiment in air, you will see this nuclear reaction. 14 nitrogen plus alpha gives oxygen plus proton. Okay, so in the ZNS scintillation screen, helium will have bigger spots, whereas proton will have smaller specks, kind of thing. And you can figure out it's not alpha particle, it's proton which is coming out. Okay, and this was, to be honest, I think I read in some article, this is the first nuclear reaction. Alpha plus nitrogen gave off oxygen plus proton. And what happened here? This is the first time someone changed an element from artificially. Okay, it was like a dream of alchemists, right? They wanted to make gold, so it cannot be done with any chemical reaction. Okay, if you want to make gold from other elements, you have to do nuclear transmutation. Okay, so this was the first nuclear reaction, and this particular reaction is honored in New Zealand's postal stamp. Okay, so is my nucleus contain which charge? Positive, and proton is positive, right? So we are done, right? We figured out fundamental elements or fundamental particle, or is there any other fundamental particle in the nucleus? Huh? Huh? Subatomic. Which subatomic particle? Huh? Neutron and neutron and proton I just mentioned. So neutron just left, right? Okay, so how can you guess the presence of neutron? What happened is that so now we know that proton, okay, so nucleus have proton, and it has a mass of hydrogen ion, right? So if you try to increase, if you go to the second element, okay, 2H, which is helium, right? So its mass number should be 2 times the mass of proton, right? But we figured out it's 4 times the mass of the proton. Okay, fine. I go to other element, lithium. It should be, if I somehow my formula works for 2 times, it should be 6 lithium 6, right? But it is 7 now. Beryllium 4 9. Okay, so something is weird going on here. Okay, so something there has to be something in addition to proton. Okay, you can guess the presence of neutron. So there was some historical thing which I will not go in great detail, limited time. So only thing I wanted to tell is uh, so whenever the alpha particle hit these elements like beryllium, boron, and lithium, it produced a highly penetrating radiation, okay, which was not deflected in electric field and magnetic field. So most commonly you just say, okay, it's gamma. It has to be a photon or something like that. So that was the case. People were thinking that it was gamma radiation, but later the daughter of Madame Curie, Curie, they discovered that this unknown radiation, whatever this neutral radiation, they kicked out proton from paraffin. Okay, and based on these things, later Chadwick did more experiment, and it was little bit unlikely that a gamma photon will eject a proton from paraffin. Okay, if you measure the kinetic energy of the proton, so they did the calculation and they figured out there has to be 50 MeV gamma ray to kick out a proton. Okay, why is it? And okay, let me just go to the next slide and I will explain it more. So what happened here is that why a neutron can kick out a proton from paraffin. Okay, so now we know that neutron and proton are of equal mass. Okay, so it is similar to your class 12 problem where you think of two equal masses, right? If you imagine balls of two equal masses, one ball is moving, okay, it hit the ball at rest. What happens to the ball at rest? It starts moving, and what happens to the ball which was moving? It comes at rest, right? So now what you are doing is that you are hitting neutron to paraffin. What paraffin is mostly made up of? Paraffin is wax, right? Hydrocarbon. So lots of hydrogens. Lots of hydrogen means lot of protons. So you hit the neutron, you hit the proton with a neutron, and a proton comes out. So this was actually happening there. Okay, so they analyzed the recoil energy of the proton and revealed that there has to be some other radiation which has a mass equal to mass of proton, and later on that's how the neutron was discovered. So there is a polonium source alpha particle which is hitting a beryllium target that give off neutron. Those produce neutron hitting a paraffin, lots of hydrocarbon, and that ultimately gave off proton, and that you keep on moving the GM counter, okay, such that you can figure out the range of the proton, and that's how you measure the kinetic energy of the proton emitted. Okay. So anyway, I think James Chadwick got Nobel Prize for discovering neutron. Okay. So moving on fast forward here. So after the discovery of, we started with atom. Now we know nucleus, and we know that nucleus is made up of proton and neutron. And this is the picture it looked like. So earlier you had Thomson's model, where you say that your entire positive charge is distributed like a watermelon and electrons like seed. And then after discovery of nucleus, you say that your entire positive charge is concentrated as a point charge, okay, point size, entire positive charge, and all the electrons are orbiting, okay. However, nucleus is not that big, okay, although I just, so not to scale, I mentioned not to scale, okay, because what is the size of atom typically? Angstrom, 10 power? Huh? Okay, and what is the size of nucleus? Femtometer. Okay, so 10 power 5 order difference. Okay, 5 order difference. And what happens? This nucleus, after discovery of neutron and proton, we figured out nucleus is made up of neutron and protons. Okay, so are we stopping here? Actually, no. So most of the present day high energy physics experiment are the scattering experiment. So Rutherford experiment, I would say, is the mother of all the scattering experiment. High energy. What we do in high energy physics experiment, you collide two beams, you do a scattering, and you measure. You build up a, detector in entire all the different angles. Okay, or you make the detector cylindrical, homogeneous. So this was just a beginning of the quest of fundamental. So let me just try to add one concept here. You all of you know a de Broglie wavelength, right? Wave particle duality. I mean, because people are here from different background, so I'm just trying to repeat it here. So we know that all those so-called quantum particle or very small particles, they exhibit wave particle duality. They can be wave or particle, right? And suppose the particle, what we call so-called electron, a particle like, will have a de Broglie wavelength attached to it, which will be the wavelength will be equal to h upon Planck constant divided by the momentum, right? This you all know, right? And if we think of a high energy electron, and if I try to write the energy of the total energy of the electron, what you will do, E square is equal to P square C square plus rest mass m square c to the power 4, right? And since it is high energy, okay, its momentum is very large, so its mass as compared to this momentum, I can neglect it, right? So I can say that E is equal to PC, roughly, right? I can neglect in front of the PC terms, okay? So I get the E is equal to PC from there, and I can infer my momentum as P is equal to E upon C, right? All of you okay? Okay. So I can say that lambda, whatever my de Broglie wavelength, is equal to hc by E. Okay, just playing along with this equation. And hc is a constant, Planck constant multiplied by the speed of light. I am not in the SI unit, I am in some unit which is comfortable to me, where I measure the beam of electron in MeV and I measure the dimension of the nucleus in femtometer. So I try to choose this unit. Although this is HC is 1.98 into 10 power minus 25 joule meter, I just played along with the units. Joule I converted to electron volt unit. That's why I told you to remember 1 eV is equal to 1.6. So from there you can get, and meter to femtometer is easy, right? 10 power minus 15. That's all. Nothing much. No fancy thing. Okay. So the question is that, can you calculate the de Broglie wavelength of electron beam energy of 190 MeV and 420 MeV respectively? Okay. So since the time is running out quickly, and so I will just tell you the answer. You can do this exercise later. Okay. So answer is, it's 6.53 femtometer for 190 MeV beam of electron and 2.95 femtometer for 420 MeV. Why I did this exercise, you will see it in a moment. Okay. So this is one concept, just to remember. Okay. Now, what you want to do is that, you all have done this scattering experiment in single slit diffraction, right? So this one dimensional slit. So, and then this is a circular aperture. So if you take a monoenergetic beam, that is laser, and there is a circular aperture, what do you see? A bright spot, and then a dark spot, and then a small faint bright spot, right? So if I try to plot this profile of intensity, okay, as a function of theta, so what you will see is that your intensity is maximum at 0, and then theta equal to 1.22 lambda by d, what you will see a minima, and then a maxima, it appears then what happens, second minima will happen at 2.23 lambda by d, right? If you try to do with a single slit, it normally happens at lambda by d, 2 lambda by d, 3 lambda by d, right? But it is for circular aperture. It is corrected for the circular aperture. Okay, just keep that in mind, that for circular aperture, first minima occurs at sine theta equal to 1.22 lambda by d. Just note it down. Okay, so from this, now can you connect both the things? Okay, these two are given. Now you connect both of this to figure out how we can figure out the size of the nucleus. Okay, what do you need for diffraction to happen prominently? You want the size of the aperture to be roughly of the same order as the size of the wavelength of the light that you're using, right? So that's exactly why. Now let me just connect the two concept I just mentioned. Is why I choose high energy electron beam. I wanted to probe nucleus as my scatterer. Now imagine nucleus as your scatterer, right? You want to go to that wavelength, your wavelength to be of that order. So that's why you choose these beams, okay, because you can probe that distance, okay? And your nucleus is an obstacle or your circular aperture, okay? So this is what exactly it was done. So it was not just a random number which I gave you. That's why I asked you to calculate 190 MeV, because there was a famous experiment done, electron beam scattering in SLAC. What they are doing is they were electron beam, and they deflected it. They put it under a slit. Again, they deflect. Why they are doing so much deflecting and bending is to reduce some sort of radiation. It's called Bremsstrahlung. Okay, if you just try to put it there along the beam line, there is a lot of Bremsstrahlung radiation. Okay, so you want to filter out all those Bremsstrahlung radiation. And ultimately, you have a pure electron beam which is hitting a scattering chamber, and there is a spectrometer or there is a detector connected which you can rotate, right? Does this remind you of any other experiment? Just now we read Rutherford experiment, right? It is a scattering experiment only, right? You had alpha particle, a target, and a detector. Same thing is happening here also, right? There is an electron beam coming, there is a scatterer, and there is a detector which is moving, right? Nothing fancy. Only thing is that my energy scale, I just scaled up. Detector thing, I made it bigger detector. Okay, so this is how I zoomed it up. The picture is zoomed up and the schematic is here. You can see so mostly it is done with several gases like nitrogen and oxygen or something like that. So you want to make it as a gas chamber, and this is how you do experiment. And this is quite big. Dimension is quite big. What do you expect if I try to plot as a function of scattering angle? What do you expect?
Sinusoidal.
Huh?
Sin theta is 1.22 lambda by d.
What you will see?
Sin theta is 1.22 lambda by d. So it must be sinusoidal also.
It must be sinusoidal. Okay. Okay. So you saw the intensity versus scattering angle, and first thing you should see is there has to be a minima at, as he said, 1.22 lambda by d, right? There has to be a minima. So you observed a minima here. Okay, you are doing a diffraction experiment, and so this was done with the oxygen nuclei with 420 MeV, and this was done with carbon nuclei 420 MeV. And you can see for oxygen nuclei, the first minima occurs at roughly at 45, and again for carbon it's 50 degree. With these information given, can you figure out the size of the nuclei? Okay. The question is the answer is obviously yes, and I'll let you wonder till lunch. Okay, we'll come back in the tutorial session, and we'll calculate the size of the we'll calculate the nuclear radius from these two formulas. Okay, we'll review it again. Okay. Okay, let me fast forward my quest. Okay, the story was the quest of fundamental. We went for we went to search for atoms, nucleus, neutron, proton, size of the nuclear radius. So now you are seeing that my experiment is becoming larger and larger. There is a need of high energy. Why there is a need of high energy? Because you want to probe smaller distances, smaller and smaller distances. So that's why we make bigger and bigger accelerator. Okay, and that's how electron, proton, neutrons are discovered. There's one more important thing for you guys: positron discovered. Okay, so positron will cover in a moment. Okay, and then neutron proton story does not stop here. People did experiment. People collided electron, or I guess with on proton. Okay, and they figure out the existence of quarks. Okay, in a similar way. I will not go in that detail. Okay, only thing is that there was some quarks discovered. So I just wanted to bring your attention to one important thing, which was neutrino. How many of you are familiar with neutrino? Only one, two. How many of you are not familiar with neutrino? Okay. So neutrino will see. Yeah. So neutrino, what happens is that it mostly in mostly in no, I will not say day to day life or in day to life. I think in bananas, right? There's potassium 40 which goes through beta decay, and neutrinos are emitted. Okay, and there are also you are getting lots of neutrino from atmosphere, sun, all those things. But anyway, in context of nuclear physics, neutrino mostly you see in beta decay. Okay, what happens in beta decay? A nuclei transforms into another nuclei, and it gives off electron or positron. Okay, for simplicity, let's take this example for electron. So I started saying that for two body decay, it has to be a monoenergetic, right? I will not do this calculation 5 minutes, but trust me, okay. If you still have if you still have query about this equation, you can ask me in the tutorial. I can solve it. I can derive it. So if you try to calculate the energy, kinetic energy of the electron or positron emitted, you can easily calculate is mass of A square minus mass of B square plus mass of electron square divided by 2 into mass of A. Isn't it everything constant here? Is there anything variable here? If I have a nuclei, I know its mass, it's fixed. If it transmuted to another nuclei, MB, its mass is fixed, right? Electron mass is fixed. Everything is fixed. The electron which will come out will have kinetic energy fixed. Okay, in a two body decay. That's how I was saying about alpha particle. It will be mostly fixed. So anyway, so if I try to now in my experiment, if I try to measure the electron energy, what you should observe? If your detector has a very nice resolution, ideal detector, okay. So you will see a straight line or Dirac delta, or if you have detector resolution is there, a very tiny Gaussian here, okay. But ideally you will see a straight line. I mean a Dirac delta kind of thing. But that's not what we observed. We observed a distribution. Okay, it starts from here and it goes towards end. Okay, what does it tell you? It tell you that it's not a two body decay. It's a multi-body. It can be two more than one particle at least should be emitted. Okay, so let's not make situation complicated. At least one. It should be a three body decay, and the third particle is we cannot detect it. Okay, I mean it's somehow it's escaping. It's so that particle is called neutrino. Okay, and okay anyway. So neutrino was, I will not go in great detail about just one thing. I will say that how neutrino was discovered. So there was compelling theoretical indirect evidence of neutrino, right? In the beta decay experiment just now you saw. You expected a Dirac delta like of curve and you saw a continuous distribution, right? So there was a compelling evidence of neutrino, existence of neutrino. But there was no direct detection. So there was physicists, they tried to detect neutrino. Why it is so difficult to detect neutrino? Huh? Large path length. Okay. Ask this question. Write it down. Ask this question in the tutorial. Okay. Why neutrino is very difficult to detect? Huh? Lifetime is very large.
Weak interaction. Weak interaction.
Okay, very nice. So it interacts only weekly. Okay, we'll come to his discussion. Okay. So anyway, so what happened is that there was one experiment designed. So there was a nuclear reactor which gives off lots of anti-neutrinos, electron anti-neutrinos. It hit a water target mixed with cadmium chloride. Okay. And let's not go into detail. Anyway, what is happening in antineutrino plus proton, it gives off neutron plus positron. It's like your beta plus decay. So if you put electron neutrino here, it will be a beta plus decay, right? Proton going to neutron plus positron plus neutrino. I just put this side. So what happens if your neutrino hit the proton? The water target means lot of protons, right? Hydrogen. So it gives off neutron and positron. Whenever a positron comes, it annihilates antimatter, right? It annihilates and gives 2 photon. Okay, and the both of photon will be 0.5 MeV each, and this neutron is absorbed by cadmium, right? In your nuclear reactor, you put cadmium rods to absorb neutron. Similarly here, cadmium absorbs a neutron and it gives, it goes in excited state and gives a delayed signal of a photon, which comes out after 10 microsecond. That is a very nice signature, that you get 2 prompt photon and a delayed photon after 10 microseconds. So that is a very nice signature of measuring, identifying neutrino. So anyway, it was, and it is very nice. One story, it was told by one of my mentor. So what he was saying, it's called $1 million particle because the entire experiment setup costed $3 million. And after running for several years, I think I forgot to mention how many years, they detected only 3 neutrino events. So 3 neutrino at the cost of $3 million. That's why neutrino is called $1 million particle. Okay, anyway, coming to it, since the story started with the quest of fundamental, so we now figured out your proton and neutron, right? It is made up of quarks. Which quarks? Proton is made up of up, up, down, and neutron is made up of down, huh? Up, down, down. Okay. So first, okay, these 2 quarks. Then you discovered electron, and we discovered neutrino. Is it? That's it? It happens to be very weird thing happened. It happens to be nature on most of the times. Most of our universe is made up of this. Okay, I mean whatever things that you see, it happens to be nature give a second and third copy of this. Okay, so you can ask me about this later. Why? It was just discovered. It's not why. There are 3 generations, and there are force carriers, like strong force carriers are gluons, electromagnetic force carriers are photon, W and Z bosons for the weak interaction. But normal matter that we see is just a 5% in the entire universe. There are lots of 95% is dark energy, dark matter. We don't know anything about it. Okay, what it is made up of. So many unresolved questions. So this is one thing. And I said, let me skip this. I will come back later. So about antiparticles. So this is the thing I just showed about the particles. There are another antiparticle of it. There is U bar up up bar, and there is electron. Electron antiparticle is positron, mu minus mu plus. So there is particle copies of those things also. Okay. Anyway, so my time is up for this lecture. I will pause here. That's it. Yeah. If there is any question, you can go for a break, or I will go for a break. I don't know.
Said that it's a Gaussian function.
Huh?
In neutrino, you have said that it is like a Gaussian or direct delta curve.
Direct delta theoretically.
It is looking like a Heaviside unit step function curve. And I recently read a paper about particle physics. So even in Crane, they have updated that it's a Heaviside unit step function.
Which one? Neutrino?
Yes, yes. Theoretically,
No, not at all.
it's looking like that.
No.
That one.
No.
Okay.
Okay. We'll discuss it. Okay. Anything else? So let's take a quick break, and we'll come back because again I have to speak for 1 more hour.